Okay, so we will start. So, just one point to clarify that the next hour, that is 11 to 12, you don't have classes, right?
Yes, sir.
Yes, sir.
Mm. So we will continue and finish the DP thing today. I'll give you a break in the middle, but then we'll continue and finish the DP thing today. Okay, so let's start. So last day we had like identified the recursive formulation for obtaining the shortest path between every pair of vertices in a directed weighted graph. Okay, so this was the Floyd's algorithm that we last day discussed. So, and you can easily see, if we look back into the algorithm, you can easily see that the complexity for finding the shortest path between all pairs is how much?
O of n cube.
O of NQ. And this is every case, right? So in every case, you have this complexity. Now, what was left to be done was to identify the shortest path itself. So we have identified the path matrix, the shortest path, sorry, the distance matrix, the shortest distance matrix that we have already identified. What was left to be done was to identify the path itself, at least one of the shortest paths out of the many. So we have already seen examples where the shortest path has been shown to be non-unique, and therefore we are interested to identify one of the many shortest paths. Okay, so the Floyd algo part 2, finding the path itself. So this is our task. So what will we assume is that we build a matrix Pij. Let us call this the path matrix. Now let us construct the matrix as follows. This is the highest index of an intermediate vertex on the shortest path between Vi to Vj if at least one such intermediate vertex exists. And this is zero if no such intermediate vertex exists. Now, how will you modify your small pseudo code fragment that we wrote last day in order to compute Pij? We can simply modify that code, right? So what was our initial code? Let's call this fluid part 2. There are the number of nodes. Then there is the weighted adjacency matrix. Then there is the distance matrix and also the path matrix. Now this is what is getting added. Okay. Now again, same like earlier. Pij initialized, D initialized to W. What do we do?
Increase Pij by 1.
Increase Pij by 1.
Pij equals K.
Equal to K.
Very good.
Equal to
Yes.
K.
I want the largest intermediate on that path. I keep on resetting this. Okay. And anything else?
Update Dij
Yeah,
to Dik plus
Dij.
Dz.
Yes. That's all. Okay. So this is how the path matrix is built. Okay. So if you look at the example that we started off with, so let's rewrite all the matrices now, the graph as well as the matrices. Let us rewrite everything so that it comes in front of our eyes. All of these things comes in front of our eyes. So this was
Sir,
our graph. Yes.
sir, can you please scroll a bit up? Okay, sir.
Catch me if you find me making mistakes. I'm usually never ashamed of getting caught by students. Okay, so this was the graph that we started off with. V1, V2, V3, V4, V5. Okay, So now let us recall W. This was W. And we constructed D from this, the final D.
Sir,
Hmm.
I think the weights of edges between V1 and V2 have been interchanged.
V1 and V2. Okay, so I think this is 9 and this is 1.
Yes, sir.
Okay, so now tell me what would be the entries of the P matrix. What will be 1, 3?
Sir, sir, why are we maintaining this P matrix?
Wait. Let us build it and then we will answer.
Sir, 1, 3 is 3.
1, 3 is
Oh,
3.
sorry, 4, 4.
4.
4. 1, 4. Now, can any one of you, from all that we have studied so far, help your friend understand why we are maintaining this matrix? What is this? What is so interesting about this matrix? So this is storing the highest intermediate vertex on the shortest path between a pair of nodes. Okay, the highest indexed intermediate vertex. What does that mean?
Using that, we can get the shortest path between any two vertices.
Why? Why? So
So,
Sir, we can decompose the path into vertex I to that highest valued vertex and highest valued
yes,
vertex
that is
kj.
what is that recurrence is actually getting embedded. So basically, you are factoring the the same recursive idea that I discussed last day. So basically, if you recall the two parts that I told you, okay, starting say from Vi to Vj, you want to get the shortest path. So this could be obtained by first going to some intermediate vertex Vk, and then from that intermediate vertex Vk to some other node, okay, which could be the destination node, in this case Vj. Fine. So this is the highest intermediate, okay, as per our recursion. The recursion that we discussed last day, this was the highest intermediate around which we were building the recursion, right? So that is what is exactly maintained in this path matrix. So basically, I go to Vj from Vi via Vk, and there is a short, my interpretation is that there is a shortest path embedded between Vi to Vk and Vk to Vj. So I can build the overall shortest path from Vi to Vj, okay, by building first the shortest path from Vi to Vk, and then the shortest path from Vk to Vj, and then finally connecting the two shortest paths to get the desired shortest path. That is what is being encoded in the P matrix. That's why we are storing this value of Vk. Okay. Now, later on, when you will, when we will study, like in the next week, of course, probably from tomorrow itself, Pawan will be starting something called a greedy paradigm. So this is the dynamic paradigm, dynamic programming paradigm. Okay, something called a greedy paradigm. So do you understand that you are choosing this path greedily among many other paths? There could be multiple such shortest paths, right? Any one would suffice. And here you are happy with the highest intermediate vertex. You keep that one.
Sir, I didn't get how we are, why, what is the necessity of the storing highest one?
Huh?
Yes, sir,
Storing?
for
Storing
storing the
what?
highest value. Highest
Storing the highest value. So were you there in the last class?
value. Yes, sir.
So you remember this figure?
Yes, sir.
Yeah. So what were we doing here? We were
Yes.
building the shortest path from Vi to Vj, okay, by constructing one shortest path from Vi to Vk and the other shortest path from Vk to Vj. And Vk is what?
Intermediate vertex.
Intermediate. And this is the, so all through our interpretation was, this is the last intermediate. Okay, you see, that's how we have built.
Yes, sir.
Okay, so here also we are keeping the last intermediate. That's why we said the highest intermediate. That same Vk is coming up here. There's a lot of background noise. The same intermediate Vk is coming up here. But then any such Vk would do, remember again, so this is why it's a greedy paradigm. This path, finally the path construction is a greedy thing. Okay, any such Vk will do as long as Vi to Vk is the shortest path and Vk to Vj is the shortest path. Any such Vk will do. We are greedily choosing the highest one. Okay, any such Vk where this relationship holds, this sub-problem relationship holds, should do, should serve our purpose. Okay. So now once we have this path matrix, can anyone tell me, like, so you have now studied a lot of traversal, etc. Can anyone tell me how can I traverse this path matrix to get the shortest, or let me call it get or print the shortest path between an input pair of vertices. This is a known notion. How should I traverse this path matrix? So again,
Sir,
in this case,
like
input is the path matrix. Tell me.
so for Pij, we first
Help me.
see what is the value in Pij. So then we find Pik and then Pkj. And if we find zero anywhere, we just print the values Ik or Kj like
So
that.
then
And
effectively,
recursively do that.
you are very, very correct. Effectively, then which among these three are you doing? Notionally.
Sir, in order.
Very good. So notionally, you are doing an in-order traversal on this path matrix to get the final path. Say the index of the two vertices between which you want to obtain the shortest path are Q and R. Then what to do? What is the in-order notion?
Path
The recursive path
Q to P of
Q
Q,
to
R.
P
PQR.
Q R. Very good. Then next step,
Then we print PQR itself.
print this is a concatenation operator, string concatenation operator, and then path
PQR to R.
done. Okay, so this is how you design an end-to-end algorithm to first compute the shortest distance between any pair of vertices and then also print the path between any pair of vertices. The build the shortest path or print the shortest path between any pair of vertices.
Sir, sir, we also need to take care of when P of Q comma R is 0.
We are only entering in when it is P of Q comma R is not equal to 0.
Okay, sir.
So, can you please explain what's written after print? Like,
Oh, this one.
yeah,
This will V and the index. Say the index is V1. That peak of QR, whatever is there in this PQR, this will be printed.
Okay, sir. Okay.
This one is basically PQR.
Okay.
Okay. So now we will do another interesting application of dynamic programming. So this comes handy. So I'll teach you one application and then I'll give you a homework to build the recursion for another very similar application. So this application,
Sir?
yes.
Sir, if we want to store all the possible paths, how can we proceed? Like
All
all
the
possible
possible,
shortest paths.
all possible shortest paths.
Yes, sir.
So you cannot do this. This is a greedy approach. This is a greedy algorithm that will give you one of the paths.
But if dik plus dkj is equal to dij, then we can include that as a short means in one of the answers because the length is equal.
Yeah, that is true. But then ideally that might explode. There might be many shortest paths. That's possible. You can always do that. You can always, so whatever cases you are having this kind of a, so as I say, this is a greedy approach and we are always interested in one of the shortest paths. Okay. But you can always enumerate all the shortest paths. Typically that's not a requirement of any problem. Whatever problem applications come in, most of the times what you are required is to identify one of the first the length of the shortest path, and the second is one of the shortest paths. Okay. Of course, you can try to modify your algorithm, store all the different k values, not only the highest k. That is where the greedy thing comes in. That's why I said that's greedy.
Yes, sir.
So the second problem that we will look into is related to this overall idea of sequence alignment. And many of the sequence alignment applications actually have a dynamic programming paradigm at the back of it. Okay, so the one that we will talk about is identifying homologous sequences required for the reconstruction of a phylogenetic tree.
Sir.
Hmm.
Sir, in the above algorithm, sir, if the dik plus dkj value is equal to dij, then we should update the value in pij because we want the maximum k value in the position.
So I don't get you. What are you telling?
So, for example, if there is some other k, but means like dik plus dkj is equal to dij, but we are getting a k value which is larger than the previous one. So, shouldn't we update pij?
Yeah, you can just have a less than equal to. Doesn't matter. So I hope everybody is aware of the term DNA. Okay. So, and a DNA is composed of what?
ATGC.
Yeah, base pairs. Okay. And these are A, G, C, T. And for our purposes, like we can think of this as a set of characters. Okay, that's good enough for us. Now, what is a DNA sequence? Okay, this is a section or a site of the entire macromolecule. Okay, so this is what is called a DNA sequence. Now, a DNA sequence can be exposed to something called a biological phenomena mutation. Okay, and mutation could be in the form of insertion, deletion, and a substitution. Now, whenever such mutations take place in the DNA sequence, at a point in time, a given population might have certain subsegments which undergo no mutation, and over time they become so different that they form two different species. Okay, and this point is also called the speciation. Okay, is the point of speciation. Now, once speciation happens, the sequences, the DNA sequences here in species 1 and species 2 are called homologous sequences. Okay, and our task is to construct this kind of a tree back. Species 1, species 2 is related to species 3, and so on and so forth. So this kind of a tree is called a phylogenetic tree. And in order to construct this phylogenetic tree, the first task is to align the two homologous sequences. Okay, so this is our task. So initially, suppose this was our DNA sequence. Okay, now at some point in time, a mutation can take place at any one of these sites, and this might be an insertion, might be a deletion, might be a substitution. Okay, and therefore the sequence might change, and the sequence might change so drastically that they become very, very different from one another, at which point they are called homologous sequences and are part of two different species. So now suppose we have two homologous sequences as follows. Let me call the first one H1, and the second one H2. And your task is to align H1 with H2. Okay. Now, in order to do this, you have to use insertion, deletion, substitution,
Excuse me, sir.
Yes.
So can you please scroll up a little? Thank you, sir. Done.
Okay. So insertion, deletion, and substitution, and there could be some special type of insertion which is called a gap insertion. Which we will denote by an underscore like this. Okay. Now suppose I give two alignments to you.
Sir, please scroll up. Yeah, okay, sir. Thank you. Yes, sir. Okay.
So now I ask you that which among these two alignment is better?
Alignment 1.
So somebody already answered alignment 1. So why do you think alignment 1 is better? So how many think alignment 1 is better? And why do you think so?
Sir, I think both alignments are better because my intuition tells more the matching, more the. I think it's more better.
Okay. Any other takes on this?
So alignment 2 is better because there are less mutations.
Is it? Okay. Anything else? Any other thoughts?
The alignment 2 because there are less gaps.
Any other point? So when you are doing all these things, there is something working at the back of your mind. Think about that. So you are telling less gaps, more matches. So there is something working at the back of your mind. You are trying to well form an ill formed problem. You are trying to well form if someone asks me, like, of course, since I know the answer now, if someone asks me that which one of the two alignments is better, my answer would be that this is an incompletely specified problem. Okay. Why? Because of the simple reason that you have not given me the cost of a gap. the cost or a penalty, whatever you call it, cost of a gap and the penalty of a mismatch. These two are not given to me. Okay? And unless and until these two are given to me, it is completely, I mean, it's absolutely impossible to tell which one of the two alignments are better. Now say my assumption is that the gap has a penalty of 1 and the mismatch has a penalty of 3. Okay, so these are my inputs and these are actually delivered usually by expert biotechnologists. Okay, so they understand like what should be a cost of a mismatch, what should be a cost of a penalty, etc. So these, for all practical purposes, as an engineer, these numbers are supplied to me. Okay, the cost of the gap and the cost of the mismatch. Now, in the light of this, tell me which alignment is better.
1.
1. Because what is the total cost here?
10.
Here the total cost is 10. And here the total cost is 11. Okay. However, if I change the same thing and tell you that cost of gap is 2 and mismatch is 1. So then your answers will change. So it depends on what the biotechnologist supplies you as the value of gap and mismatch penalties. Okay. Accordingly, you have to design or compute the overall betterness of one alignment over the other. So for our dry run of the algorithm, we will assume without any loss of generality that mismatch penalty is 1, gap penalty is 2. Okay. Now we will kind of start storing the characters in 2 different arrays. Let's say that this is our working example, the example that I started off with. So these are my 2 arrays, okay, that I build in order to compute whatever I want to compute. Now let us define opt ij as the cost of optimal alignment of the subsequences x I to 9 and y j to 7. Okay. Then, as you can well understand, that opt 00 will be the cost of optimal alignment of the entire right. So my final answer will be in opt 00. Okay. So how will my optimal alignment start? Let's just think of the start. What are the subconditions? What are the subconditions that can take place? See, this is the most important part.
Sir, xi equal to xj.
Xi equal to
y.
No, alignment. You are aligning. The task is alignment. So you want to say, do you want to say that x0 is aligned with y0? I have asked alignment start. How will the alignment start? Do you want to tell me that the first one of the subconditions is x0 is aligned with y0? This is what you want to say?
Sir, we are coming from the back side.
Yes, that's okay. You are coming from the back side, but think of the first step. This is important because then we will be able to build the sub problem. We will come from the back side only. Say x0 is aligned with y0.
Yes, sir.
Okay, so then now you have to check if x0 is equal to y0, then penalty is equal to 0. Else, if x0 is not equal to y0, then penalty is 1. What are the other two subconditions? It should be easy to imagine.
x0 aligned with a gap.
Very good. x0 is aligned with a gap. Okay, so that means there is a gap penalty of 2 at the first site. Last one, y0 is aligned with a gap. Again, there is a gap penalty of 2 at the first site. Now the optimal substructure part. So let's say A OPT.
Excuse me, sir.
Yes.
So please follow. Thank you, sir.
Sir, in the second case, if x0 is aligned with a gap, then what about y0? Shouldn't we consider its penalty?
Should we?
Should not we consider the penalty of y0? Like if y0 is aligned with some other x which is not equal to this.
Do we need to do that? Y0 moves one step ahead, and it might match with the site x1. We are going by array indices. Y0 might align well with x1. Isn't that possible?
It can.
Yeah. So we are going index by index. So let us suppose that A opt is the optimal alignment of x 0 through 9 with y 0 through 7. Okay, and in this case, select x0 has been aligned with y0. Let us suppose. Okay. So now what can you say about the optimal substructure?
X1 to 9 and Y1 to 7 must be optimally aligned.
So let's say there is some alignment B of x1 to 9 with y1 to 7, which is embedded in A opt. Okay. Now, can we argue that B is an optimal alignment? How will the argument proceed?
Sir, we assume that there is a better alignment than B.
Very good. Very good. So this is a proof by contradiction, right? So let's say we assume that there is a better alignment C than B. Now, if this is so, then what can we say? We can have C and x0 aligned with y0 as an overall alignment which is better or has lesser cost than whom?
A-opt.
A-opt. But by construction, A-opt is the optimal alignment. This implies B should also be an optimal alignment. Right? So this is the substructure that we are trying to construct. Now this argument holds for the other two subconditions also, the gap subconditions also. Now given this, can I build the recursion let's say first try with the easier one. Also let us define a variable p which is equal to 0 if x0 is equal to y0 is equal to 1 if x0 is not equal to y0. Okay, now tell me what would be opt 0, 0 and then the general form. So what are the different cases? X1 aligns with Y1, right? X1
Yes, sir.
aligns with Y1. Okay, and there could be a penalty or no penalty depending on whether X1 is equal to Y1. What is another case?
X0 is aligned with a gap.
X0 aligns with a gap and the gap penalty of 2 is added. And what is the third one?
Opt
Y0
0 comma 1 plus 2.
And what will be opt 0, 0 then?
the minimum of these.
Minimum.
Yes. So, and you can, of course, generalize this to the IJ case.
Excuse me, sir.
Yes.
Sir, in opt 00y, we are including opt 11 also.
That is the optimal substructure. This is where X1 and Y1 are aligned. right? This is where the x1 and y1 are aligned. This is the case. This is where x0 is aligned with a gap. And this is where y0.
Sir, are you taking gap penalty as 2?
Yes, that's what we started off with. If you recall, we started off with this mismatch penalty as 1 and gap penalty as 2.
Okay.
Yeah, so is this clear to you? Somebody asked me this question.
Yes, sir.
Okay, so further clarification. So let us assume that this is an optimal alignment. Okay.
Sir,
Go ahead.
sir, when the means opt 9,7 and 8,7, like they would try to just replace the things, no, sir?
Wait. We have not come to the base conditions. We will come to the base condition. We will come to the base condition. So just trying to still understand and make this part clear to the rest of the class. So suppose if this is an optimal alignment, now this also means that this is an optimal alignment. Which also means that this is an optimal alignment. And this is an optimal alignment, and so on and so forth. So now there was a pertinent question to which we have not given any answer so far. Now, what will happen to base conditions? When will this take place? Let's say M is the length of sequence X and N is the length of sequence Y.
Sir, when we call for opt m minus 1 comma j or opt I comma n minus 1, like we have no further characters in either one or
yes. So, and in such cases, what will you do?
Sir, take the remaining characters and align them with gaps.
Very good. That's what exactly what we are doing. So I hope the others have followed what he said. So basically say we have reached end of x, okay, where I has become equal to n, but then j is still less than n. Okay? So then we fill the rest. What is the rest? How much is the rest? How much is the rest?
N minus n.
N minus j gaps. Right? N minus j gaps. So then opt mj is, what is the cost of this?
2 times n minus j.
2 times n minus j.
Similarly, the other side of the coin.
So please scroll up a little bit. Thank you, sir.
Okay. So now, once this is done, we have to just build the table. So again, let us take the same example and construct the table.
So can you show the recursion that you wrote last?
I'll show. Let me finish drawing the table. The base one or the top one?
Base one. Okay.
So the last two gaps are used to give us a dummy start. So now you will help me build the cell elements. From the recursion. So each of the values are actually a minimum of these three things, right? Agreed?
Yes, sir.
Each cell is filled
Yes,
up
sir.
as a minimum of these three things. So you see again that notion of building it from bottom to top is still maintained here, as is the typical case with a dynamic programming paradigm. And how will we build the elements?
So starting from the base
Yes,
cases.
yeah, base cases, that's fine. But do you see, like, when you do that, the elements are filled up in what way? There is an
Bottom
interesting
to top.
way. Yes, bottom to top, but then there is an in within bottom to top also, there is an interesting pattern in which it is getting filled up.
Like
If you
it's
look
an L
carefully,
shape.
diagonal to diagonal, you see, we keep filling up like this. You first fill diagonal 1, say let's call it D1, diagonal 1, then you fill all the elements in diagonal 2, then diagonal 3, and so on and so forth.
Sir,
Yes.
sir, we can also fill it by columns.
Mane?
Sir, I mean, sir, first we fill the very last row and very last column, and then we start filling the 7th column, then 6th column, then 5th column, like that.
6th column.
From bottom to top.
Yeah, of course, like you can do that. But this is a much better way of, yeah, you can go that way. But this kind of a raster allows us to remember a nice sequence in which you can fill up. Of course, as long as you are filling up with the correct recursion, everything is fine. This was just to help you out to remember. Okay, so now we will fill up the elements. What will be this one?
Sir, 0.
0. The first one is 0.
Yes,
the
sir.
left hand, this one. This one is not 0. Acha, what will be this one?
Sir, are you pointing on some box?
Oh, okay, you are not able to see the point. Okay, fine. No point showing it that way. Let me try to fill up. Acha, so tell me what will be 10, 7?
Sir, 2.
2. Okay. What will be 9, 8?
2.
2.
And you can keep on filling this using the recursion that I have just now written down. And the optimal cost is sitting here. This is the optimal cost, okay, at opt 0, 0. So this would be the optimal cost of aligning the two sequences. Now, how to get the sequence? Once we have built the table from here, how do we get the sequence?
Sir,
Huh?
sir, I have a doubt in the cell 7,2, sir.
7, comma
2.
7, comma 2. Okay.
Sir, here the value is 7 or 8, sir.
No, it's 7.
Sir, how
Because
Yes, sir.
because the alignment is matching. Penalty is 0.
Okay, got sir. Okay,
Sir, in the cell 7, comma 6.
Wait, 7, comma 6. This one, right?
Yes, sir.
Yes.
It is a mismatch, so it should be minimum plus 1.
7, comma 6. No, what is the minimum?
So we
No,
are
no, it's
aligning it
correct.
with the gap.
Yeah, we are aligning it with a gap. 1 plus 2, that's 3. 1 plus 2, it's 3. That's the minimum. This will become 3 plus 1, 4. So we'll not take that. This will become 4 plus 2, 6. This will be 1 plus 2, 3. So we'll take this. Got it?
Yes, sir. Okay.
Okay, so now how to extract the alignment path? Here, you will have to start from 0, 0. Okay. Now, you will check slot 0, 1. Okay. Now, and ask the question, is 0, 0 built from 0, 1? Okay. So this could be answered by asking whether opt 0, 1 plus, how will you build 0, 0?
Sir, gap.
Gap is equal to 7 or not. So what we see, this is 8 plus 2, which is not equal to 7. So this route was not taken. Let's see slot 1, 0. So then here opt 1, 0 plus, again this is a gap, okay, plus 2, whether this is equal to 7 or not. So this is 6 plus 2, this is not equal to 7. So this was also not taken. So now you see opt, slot 1, 1. In this case, opt 1, 1 plus how much? Plus P. What is the penalty here? 0 or 1?
1.
1. So We check whether 6 plus 1, and this is correct. So that means it came from slot 1, 1. Okay. So going back to the table, now we know that this one, opt 0, 0, was built from opt 1, 1. Okay. Now can you tell me the rest? This will also be a nice exercise for yourself. Tiebreakers are broken arbitrarily. Sorry, ties are broken arbitrarily. Sorry.
1 1 is from 2 2.
2 2. Then
3 3.
Sir, 3 2 also can be
Then
possibility.
3 2, sir.
okay, if there is a
Yeah,
tie, it
it's
will
a
be
tie.
broken. It will be broken by arbitrarily. Then
Sir, 4 4.
Yeah, 4 4 or 4 3.
so this is your path. One of the possible paths if there is arbitration. Be very careful when you
Sir, it
reconstruct the
should be
path.
from 2 2 to 3 2, sir, because 6 plus 1 has to be the case
You
because
check.
they are not equal.
You check. This is the correct one. You check. You are doing some mistake. I can only say that you are doing some mistake. If you are not getting this one, then you are doing some mistake.
So like if we go from 2 2 to 3 3, then there is a mismatch penalty as well. So how can both of the values be same? Because 2 2 doesn't match, means x2 doesn't match with
2
1.
2. Okay, 2 2 is this one 6, right?
Yes,
And
both of
3
them do
3.
not match.
Yes, sir. So then we go to 3 2.
Why they do not match? Because A and A are matching. So penalty is 0. So 6 plus 0 is 6.
A and C,
So it
sir.
is A and G.
No, no, you are telling 2 2, right?
So 2 2 to 3 3, sir.
Yeah, 3 3. Okay. So 3 3. What is happening to 3 3? So
So 2 of x is C, but 2 of y is A. So that is a mismatch, sir. It cannot come from 3 3. Penalty is 1.
yeah, so this one is wrong. I made
It
a
should
mistake.
come from 3 2,
Yeah,
sir.
this should come from this one. Thanks, I made a mistake here. Fine, right? This looks fine. Now the alignment still not done. How do we get the alignment? Path is obtained. Now the highlighted path is obtained. We have to use this highlighted path to get the alignment. Of course, the alignment will be generated in the reverse order. Now you start from the bottom right. So if you move from slot ij, okay, in the diagonal direction, then what does this mean?
So both letters we are taking without a gap.
So that means align xi with yj. If you move directly up, okay, to come at slot ij, then what do we do? If we come directly up,
xi plus 1 is aligned with a gap.
no. If you come directly up to the slot ij, then xi is placed in the sequence, and I'm giving you the hint, and a gap is inserted in the y sequence. Now, if you move directly to the left to arrive at slot ij, then the converse, right? Yj sits in the sequence of y in sequence of x, a gap is placed. Exactly as you are adding the penalties. So in this way, your optimal alignment for the example that we had taken would be the following. It always fills up in the reverse order. So that's how you solve a problem end to end, starting from the penalty values. You first construct the optimal substructure. So in your lab assignments also, you will get something very similar to this type of problem. Like you have to build the optimal substructure and then the recursion. Once you have done the recursion in dynamic programming, the coding is very easy. The only part is to catch the way to get the recursion. So as a practice,
Sir,
uh,
sir, I have a doubt that after we get that path along that matrix,
uh,
while constructing this sequence, we are coming from backside, right?
yes.
Sir, but can't we go from front side as well? Like when I'm going to the next diagonal box, then I'm aligning them, and if
So
I am
this is my algorithm. You change your algorithm and like if that works, it works. This is my algorithm.
sir, like in the
I'm starting
same
from
with the same path, can't we construct it from forward direction?
yeah, of course you can, but you see my path directions are opposite. I have constructed a directed path. Okay, to keep it notionally same, I have constructed my algorithm also in the same way.
Okay, sir.
So that's why I said moving left, going up, all these things will change. All these notions will change when you have, if you want to do it from the other way. It will become going down, coming from left, something like that. Okay, so the notional thing will change, and accordingly your algorithm will change. I mean, of course, slightly, but you can, I mean, you are free to do it. Once you have constructed the path, you can traverse it in any way to get. We did it in the opposite way because we notionally built the path in a directed manner, starting from the bottom to top. So Levenshtein distance, or sometimes also called the edit distance, between a pair of strings, say cat and bat, okay, is the minimum number of operations that you need to do to get the target word from the source word. So basically, again here the operations that are allowed are insertion, deletion, and substitution. Let us say cost of insertion is 1, cost of deletion is 1, and cost of substitution is also 1. Typically, you can imagine this to be a a deletion followed by an insertion. But then for the time being, let us consider each of these have a cost of 1. Okay. Now suppose you are given 2 such strings and you want to change cat to bat. So you see that 1 substitution will serve your purpose. Okay, so that means the edit distance between these 2 words is 1. So similarly, given 2 arbitrary words of arbitrary length, you have to find out the edit distance between these 2 words. This is a famous application of DP. The solution is already there on Wikipedia. If you search with edit distance implementation or like Levenshtein distance implementation, you will get the solution in Wikipedia. However, my suggestion would be to try to build the recurrence yourself, and like once you have been able to build the recurrence, write the simple code and see like if it matches with whatever is expected from this particular task. So people who later on move to areas of NLP and information retrieval, they will find that this kind of an application is very much useful in many different scenarios. So this is anyway a good application to try, and is like a direct notional advancement of the algorithm that we discussed today. So this is also a type of a sequence alignment problem where you want to find out the distance between a pair of strings. Okay. Typically we have dictionary words between which we want to find out the edit distance, but like this can be generalized to any pair of strings. Okay, so
Sir?
we'll stop here. Yes.
So in DNA sequence, the operations which we were allowed were insert, delete, and substitute. But with the
Yes.
we only used gap and mismatch. Why is that so? Means
yeah. So our task here was, so the second part is something that we have not done. Our task here was alignment. We wanted to do alignment. We did not want.
wherever there was a gap, so we would insert the corresponding character from other sequence.
Yeah, so we did not want to, like our question was a little bit different. So there our question was like, I want to align these two pair of strings. And the question that you are asking is like, what sort of deletion, addition, and substitution should I do to get, say, this sequence from this sequence, or the vice versa, right? This is the question that you are asking now.
Yes, means
Agreed?
only defined the cost for two operations, right? Insert and delete we did not.
Yes, here, because here our task was alignment. Now if I slightly change the task and tell you that, okay, tell me the total number of insertion, deletion, and substitution that I need to do to get this sequence from this sequence, or this sequence from this sequence. This is exactly the task that I'm giving you here.
Okay, sir. Understood.
Sir, in
Sir?
substitution, we are only changing the string that we want.
Yes. I substitute C with B.
That means we are not changing the second string.
No.
Okay. Okay, so thank you.
So here there is a notion of source and target. Source, as I said, source and target. So given the source, you want to find out the minimum number of operations and therefore the cost of those operations to go to the target. Say the source is cat, I want to go to bat. And as usual with any other distance, edit distance is a metric and also it's symmetric in nature. There are some distances which are not symmetric. Anyway, let's not talk about them in the algo class. Later on when you come to higher semesters and we meet again for some elective, we can talk about them.
Sir, here we are doing only insertion and substitution.
Where?
Sir, I mean, we can do the problem by only inserting and substituting some letters.
No, tell me again.
Sir, I'm saying that we can transform from source to target by only inserting and substituting, sir.
Is it? Is it?
Okay, if length is greater, okay. Yes, sir. We also need to delete. Yes, sir. Understood.
That's what I said. The input strings are of arbitrary length. Okay, so we'll stop here. I'll upload all the lecture materials for all these days.
So what about tomorrow's lab?
That is cancelled.
Postponed.
Yeah, that is postponed to the November 6th slot. That's what you wanted.
Yes, sir. Thank you.
Sir, topic is postponed or like topic will be that
Topic
next
will be, no, topic will, it's just a 1 week lag.
Okay,
so
sir.
next week, the same topic, DP, next week we will have the assignment. It's just 1 week lag that we will run now.
Okay, sir.
So there will be a normal class tomorrow in that slot?
No. No classes in that slot.
Thank you, sir.
Because we are having a class in lieu of it. So no normal classes in that slot. Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.